Okay. Hello, everybody. اليوم week 6 of the mission semester in the compilers course. اليوم we will try and cover شوية ديال compiler optimizations. We will try to do it really quickly and as fast as possible باش عزوز يبقى له الوقت يكمل السيشن ديالو لحقاش apparently السيشن ديال عزوز is very very important. Okay. So كما نحاولوا like thinking about this is that the first thing اللي بغينا نفكروا فيه when talking about compiler optimizations هي إن okay so we did كما هضرنا في السيمانات الفايتين هضرنا على lexeme parsing. You have like a syntax you have a syntax abstract syntax tree. You can generate like control flows, data flows out of it. You have an intermediate representation. Now you have something that actually works just by walking that IR or generating code out of that IR. You will be able to generate binaries, and those binaries can be run. Sad part here, and this without optimization would be very slow. Okay, so if this is slow, what can we do? Now, what sort of things like that the compiler would be doing to optimize this code? So الحوايج اللي need to keep in mind. أول حاجة like optimizations have like a different scopes. Like some optimizations operate just on we call them local optimizations because they operate just at the basic block level. Like عندك a block which we can anything that is like a simple block of instructions gets operated عليه optimization. We'll see a couple of examples of this. And then we have some things that are called like global optimizations. هما الحوايج اللي we optimize across modules with the functions. Difference ما بين هاد الجوج هادو هو أن for local optimizations they are pretty cheap to do. Like the context اللي خص الكومبايلر ولا الoptimizer يعرف is just around that block. While for global optimizations the context اللي خصك تعرف خصو يكون داكشي cross function. So it needs to know a lot of information about like the data flow and the control flow across multiple functions. So it can get you to crunch a bunch of numbers and do a lot of computations to decide whether an optimization pattern or an optimization idea applies or not. The benefits for local optimizations can be like pretty small. optimize one log, one basic block, ولكن for a global function level optimization you can optimize like functions away, or you can like the idea is that the benefits can be like pretty huge. So like just keep in mind really like كاينين شي حوايج can operate on very small scope, and then some like require more information, and then optimizers have to be smart into like picking which of these things to go ahead with. Right, optimizer on itself needs to think about a couple of things. What sort of things need we can optimize, like and had the information and on a tree of instructions and a flow نتاع الداتا كنعرفوا الداتا كي كدير flow في البروغرام وهنا الفلو ديال الكنترول كنعرفوا كي كدير flow في البروغرام. Like what can I optimize from this point on? Like the most basic thing اللي كنحاولوا ديما نحاول نحيدو هو okay let's try and optimize so that I have less code to execute. If I have less code to execute I'll likely be faster. But you can think of it as like عندنا جوج نتاع الباينريز اللي هما في حال exactly the same, right? And then one of them has one less instruction to run. This would potentially mean really the other one is faster. حقاش عنده one less instruction to run, by whatever faster means in this context. Sometimes like the optimizer would decide, okay, so I want to do less jumps, because jumps are things that are kind of bad. I don't know if you've been taught this, but like CPUs like to operate in like straight lines. ما كانش أي حاجة اللي هي a straight line, either like read memory in a straight line, read like go through instructions through a straight line. It's nicer for CPUs لحقاش they can like prefetch a lot of this information and then prepare things ahead. Like you can have less branch misprediction. like the CPUs are very complex and they are designed to execute things really really fast, but they have to do a lot of things that are hand. I'm not gonna say hand wavy, ولكن um, they gotta sometimes predict شنو هتحاول تدير نتايا and then try and do it, and then if you don't do it they'll have to clean up and then do the actually what you did. In most cases this yields like faster things, not slower things, but like if you do, like in the case like if you traverse an array it's much faster. It's directly it's a direct sequence of instructions. We can pre-compute offsets, we can do a lot of things. If you traverse a linked list, there's nothing that the CPU could do. Like you're jumping all around memory, so it's very hard to optimize anything, and they have no idea what are you trying to do. So we like jumps here could be like jumps in memory, or could be jumps in the control flow structure called sometimes we want to remove like redundancy, like if something needs to be computed more than once, might as well just compute it once and reuse it, as long as it doesn't affect the overall output of the program. Sometimes we want to optimize, we want to reduce the strength of some operation. You can think of this as that some operations are more expensive than other operations. And actually operations like division per se, it's way more expensive than just performing simple addition. So addition and subtractions are instructions that are much cheaper to do than performing division. And you can have a bunch of instructions that are considered to be like much more expensive, and the compiler would look at things and say, can I do this in a way that is cheaper? So an optimizer would look at this and would keep in mind, okay, can I do this cheaper in thousands and thousands of places across the programs? It will try and do like very small optimizations, and this will yield like faster code. الحاجة اللي مهمة بزاف اللي يحاول الكمبايلر يخليها in mind هي ولا الoptimizer in mind is that the output of the program shouldn't change. And the output here is the behavior del program ديالك. So if you have a program that takes A and B as arguments and then output the sum of A and B, regardless of the optimizations, في الآخر بغينا نشوفوا السم ديال A plus B. If the optimizer optimizes this and does something else, that's not a very great optimizer. ما بداش داكشي اللي بغيتي يدير انت. Right? So that's the key idea into an optimizer. It needs to keep the behavior the same, but it'll try and like minimize like redundant things, or like remove instructions, or tries to rewrite things in a way that keeps the semantics ولكن makes it faster. Like إلى عندي ضربة في ثلاثة, I can make it into A زائد A زائد A because that's cheaper to do, or because I can decide that on this specific architecture, or the machine architecture, like 3 times doing A plus A plus A is cheaper than doing A times 3, for whatever reason. This is not always true, but this is an example. Any questions, Selena? Okay, I'm gonna assume that this is Selena is pretty clear. But I expect questions, otherwise like we're gonna finish this quite early. All right, let's go through some techniques. So هنا غنشوفوا like some of the techniques that a compiler would usually go through and try and do, and let's see like sometimes behind the hood about like what is actually going on. So this code is actually like this some function that is called foo. The technique here in compiler lingo is called loop unrolling. And you can think about it like this. You have a loop that is trying to execute something 90 times, right? And it's calling a function called foo with the argument being x with loop. The compiler could decide to say, let me unroll this loop in a way that I can just call foo with x, then x plus 1, then x plus 2, and then I could continue my jumps and do it 3 times. Right? This would yield a program that would like have to jump 30% less. All right? Aziz?
Yeah. So وقيلا جاوبتي في the last sentence. I was I was mainly asking how will the second first question is
Mm.
this is like commonly used, meaning like your compiler might do this very often, which the technique is widely used. Second part, how second part can be faster than first part.
Yeah, so again, like إلى رجعنا قبل آخر slide قبل من هذا, one of the things that we will try to optimize maybe is less jumps. Now the control flow هنا, if you write this loop in assembly, it's a lot of like do this something sequence and then jump back and then do it again and then jump back and then do it again. This is the assembly for this, right? Ideally, we want to remove that jump back, jump back. So what you did is like you inline 3 instructions and then you jump back every third instruction, which means this will make it 30% less jumping, right? But then again, the question that you asked first is an interesting one. Like in this case, I have a perfect 90, which is divisible by 3. This is not always the case, right? I have no idea of knowing. Sometimes like that very Hadi is not sane. It's like something else. It's like 19,415. شنو هيدي الكومبايلر ذاك الكيس؟ Like compilers are like speculative most of the time. Like they will try and look at the data and see if they can do something about it. And sometimes they hard code the code. Like maybe we can choose to unroll this up to 5. Like we do fx, x plus 1, x plus 2, x plus 3, x plus 4, and then I do x plus 5 here, and then I only jump here and do it like 20% less. This is
Yeah, so واش كيخدموا heuristics ولا مثلا كيف ما قلتي hard coded, meaning people writing compilers, they do benchmarks and they decide, okay, for some like for 100 we do 5 or something like this.
I guess it's a mix of both. Sometimes we will have like set instructions, especially for compiled languages that don't have a runtime. We will have set things to do. Like if you see this, do that, basically. Um, in the case of like runtime-based languages, you can optimize it. Like think about it like Java مثلا. Java could decide because it has that information and it runs as a JIT compiler. It can decide, okay, if you see this pattern, which looks like, okay, the number 10 is actually a variable, right? ولكن you always keep seeing 10 here, right? I might try and decide and say, okay, so I can assume that this is always 10 and then I can just generate the code for Hadi 10 and then I can unroll the loop being like with x plus equals 3. So it's a mix of both. I'm trying here to highlight the techniques without being tied to a specific compiler, although like we'll do a lot of like things assuming C and C++. Like in the JIT compiler would have similar ideas, but would have different implementations, if that makes sense. We'll see later on about how does this probably look, and then if there are more questions we can answer. Okay. Another idea about like loop unrolling. Wherein like one model is like, okay, let me unroll this in this way. Sometimes the number of instructions is pretty low. Like if إلى الكود هذا we have like x من 0 حتى ل 4. إذا كان x موديله جوج كيساوي 0, then foo, call foo with x. If otherwise, call bar with x. So the compiler, to remove قاعد ذاك shenanigans مثلا ديال set up the loop instruction set, call the loop, and then go up and then jump back, go down, jump back, go down, jump back. It can decide, oh, let me not do this and just treat this as this, which is exactly the same. Like we can go foo 0, bar واحد, foo جوج, bar 3. Right? The generated code for this would keep, remember this, like we will keep the semantics, we will keep the same output of the code, but these, now we don't have to do any of the loop control flow settings. Right? So this is faster because it's removing the amount of jumps again, like that we wanted to do. Now we're doing less jumps, if that makes sense. And the behavior, you can see it, it's still the same. Like this is how we were about to code it. Okay, no questions. Let's go to some other thing. This is like loop unrolling, but this time تخيل دابا هاد void foo takes an array and then calls for every element in the array. We could call bar on the element of the array. Now, هذه in C++ land, it'll be very hard to optimize because I have zero idea, because the size of the array that memory is allocated at runtime, and I have no idea about how big it is. So I can't pre-compute offsets, and I can't really do anything about it. Tell the values, I have no idea about what the values are. So I'll have to spit out the proper code that looks exactly like this. Like extract like bit by bit, go fetch offset 0, pre-compute offset 1, pre-compute the offset 2, and then read the memory and then pass it to bar. And then perform a call instruction and then do it all over again. But if you have like an environment where you optimize at runtime, like في case in Java, you can do things because you have that runtime. You can observe مثلا this function, right? And you can have the runtime observe it and see, okay, so I'm always getting arrays of size 4 here. Think about it as like your dx array, where you're getting a function that takes like your movement in a x-axis or the y-axis. You're always getting left, right, top, down, but this is an array nonetheless, right? So the runtime can decide, okay, so this array is always 4. This function has been called for 1,000 or 2,000 times with always an array of size 4. Can I optimize this? Well, I can guard this and transform this into this. I will call always bar with array of 0, bar array of 1, bar array 2, bar array 3. And this is equivalent to this if the array size is 4. This will yield a very much faster like machine code, because like guess what? Once you do this, you can inline even this bar if it makes sense. And you can do optimizations at a second level in the bar at bar itself, right? But again, like one of you might ask, what if I pass an array of 5, or of 6 afterwards? Assuming من بعد مشينا ودرنا, okay, so this array changed size. So the runtime should keep track of, okay, so the change or the assumption, we call that conditional you could call it like a guard or a conditional that guards this optimization. And if the value of the length changed while calling this function, this code needs to be thrown away. And we need to call the code that looks like this, because now the conditions or the environment actually changed. And if we keep calling again the array with the same number, this optimization could be back at the table. This is the benefit of having a runtime. Sometimes, like being a compiler, you don't get this information. You can only optimize the things that you can see. Okay? باين احسن لنا. All right. Let me then let us do like to dig a little bit deeper. Let's do an LLVM primer. I know we didn't cover LLVM. We didn't cover actually any of the IR languages. We expect you to develop one. So I'm gonna give you like a very 2-slide introduction to LLVM, and it should be enough, hopefully. So when you usually see LLVM IR in the wild, if you ever go look for it, you'll find it in what we call SSA form, which is a single static assignment form, which means basically كل variable كتكون declaraيهم assign just once, and we never reuse or reassign variables. This is good لحقاش it allows some optimizations that we're not going to care about right now, and it helps with register allocation. Yeah, actually, we're not going to care about it right now. Well, the thing to keep in mind here, and IR into LLVM, and into any IR for that matter, the instructions look similar to assembly, right? But it's not assembly. It's something more portable. And they have like instructions that can do arithmetic operations, can perform addition, multiplication, whatever. They can call functions. It can manipulate the stack, manipulate access memory. هذوما الحوايج اللي كيربريزنتيو like the IR, right? Let's look through a couple of examples. Like these are select instructions that we will use like في هذا الكورس هذا. So like a store, as the name implies, like it will write the values to some stack space or some other memory location. A load will read the value from some memory location. A branch instruction will direct the control flow between like different blocks. Like we have basic blocks, we can branch and then move the control flow into one branch or another. We have an I CMP, which will compare integer values, and then from there we can use it to determine فين غيمشي الكنترول flow واش لواحد جهة لواحد جهة. We have like instructions like mul, sub, which will be used to perform integer operations like multiplications, subtractions, additions, and whatnot. We have ret instructions, which can return the control back to the callee function. Like إذا كنت في هذا الانستراكشن وصلنا الرت, we will go back to the whether we will go back and continue executing from the latest saved address on the stack. We have a call instruction which invokes functions. It can facilitate recursion. It's an abstraction over a couple of assembly instructions. It's usually translated into a couple of assembly instructions, but this is really handy to look at as a just call a function. We have this kind of phi function, which you will see a lot, which sets values based on which branch جيتي منها. We'll see examples of this, but like فاش كيكون عندك control flow جاي يقدر يكون جاي من one branch ولا من another, كتقول okay, I want to assign the value of this variable based على حسب منين جيت. If I come from branch A, I will assign the value to this. If I come from branch B, I'll assign a value to that. We'll see examples of this, but just keep in mind that there is this kind of instruction that is called the phi instruction. Okay, هذا البرايمر ديال LLVM. So down the line من هنا في الكورة غنشوفوا like some LLVM instructions to see like how code behaves, whether when optimizations are enabled or not, and then we'll using this we will be able to read LLVM instructions. Okay, continue on. كاين واحدة من التكنيكس the compilers use a lot is something called the constant folding. Constant folding is an optimizations where we can like replace constants by their values at compile time. So إذا كان عندي مثلا واحد الانستراكشن x كتساوي 200 مضروبة في 100 ناقص 10. Okay, this is an assignment. I'm assigning this value x كتساوي 200 في 100 ناقص 10. If I have this instruction, the translation data, right? And LLVMIR is, okay, take 200, multiply it by 100, and store it at value A. Take A minus 10, like subtract 10 from A, and store it at B, and then store B in memory location yet X, right? So this is like the LLVM representation. Your optimizer could look at this and say, well, this is a constant. This is a constant. Let me compute this. This is still a constant. I can recompute this. And then the answer is 19,990. So X is 19,990. So if your optimizer is on, 3 instructions could become just 1 instruction. I want to store 19,990 into X. And I can derive this from compile time, at compile time. And I don't have to run all of this. Okay? بين هادي. Everybody else? بين هادي. I'm checking because لحقاش مازالين كاينين larger LLVM blocks and I want you to be comfortable reading this. Any questions هنا؟ All right, I'm going to assume that this is clear. All right. Another technique is called common sub-expression elimination. All right, نشوف الفانكشن عجيبة اللي هي foo. It takes 2 arguments, A and B, and it creates an internal variable called C, and it's the result of computing a plus b times a plus b over 4. We compute this value, and then we return c. Okay? How can we optimize this? As a human looking through this, how can you optimize it? إذا كنا قلنا لك أنت optimize بيدك. How would you optimize it? Mehdi?
نقدروا ديجا نحسبوا هذيك a بلس b مره واحده وبلاص ما نستوريو ديك الاوبريشن كامله في سي نريتورنيوها نيشان.
Story you have seen, return narration.
لا بلا ما تستوريوها في سي
Oh yeah,
لا نريتورنيوها نيشان.
yeah, that's true. We can do this, but like think about this as like return heady. You don't have to think about C, but computing a plus b once is a very good observation. This is good. We can do this. Mehdi?
We can replace a plus b times 2 and then divided by 4.
Times 2? Why is it times 2? And a plus b times a plus b. You can't replace that with a plus b plus 2. Unless my math is failing me though.
Yeah, you're right, sorry.
But a plus b plus a plus b.
Yeah.
Okay, that's fine. So كما قال مهدي قال لك up a plus b, we should only compute it once. What can we do else? محمد صابر كيقول لك باو. What do you mean by باو? مهدي أنت بغيت تقول شي حاجة ولا من قبيلة هذه بقات مزوز؟
لا من قبل sorry.
Okay. What do you mean باو? Can you speak up?
الطبقة الهامة.
الطبقة الهامة. محمد صابر, can you speak up?
زعما تحسب دي ا بلس بي ولا باور زعما باور
باور ديال a plus b.
طاف واحد الفاريابل مثلا سي ايكوالز ا بلس بي ودير سي باور سي.
شنو دير سي؟
سي باور سي.
C power C?
وي
How would that work? What do you mean C power C?
زعما عرفتش كتسمى بالعربية
أس.
وي الأس وي
سي أس سي.
وي.
علاش تجي سي أس سي؟ I don't think أجي سي أس سي.
المهم غير فكرت فيها صافي.
Yeah, it's fine. But like, think about it like from the optimizer's perspective. بغينا نخليو الريزلت يبقى the same, right? We just want to optimize it. Like a plus b times a plus b. The optimization اللي عندنا دابا هي okay. Let me just compute a plus b once and reuse it. So let me give you another hint, right? Another hint is this. So this is what the non-optimized LLVM code would look like. If إلا كنتي كتراني الكود ديالك بلا optimization, هادشي علاش I'm using this to make a point. And now we need optimizations. We can't really run code without optimizations. Otherwise, our programs would be very slow. This is the code that your compiler would spit up. All right, let's read through it. Like I'm gonna store A, right, and B, which are the variables, right, into some addresses. Maybe this can be skipped because, yeah, this is not terribly important. We just store I into like a that address and then we're gonna read it back.
I think هذاك الباساج فالور.
Yeah, we don't really care about this. I cleaned up a lot of this code before, and maybe I should have cleaned up this as well. This is not all the LLVM code that gets spit up. I had to clean it up شوية باش to just make the things that make sense available. Otherwise, we're gonna end up like reading a bunch of code that we don't really need. So like اول حاجه غيدير الكود ديالك هو انه كاين واحد فاريابل زيرو وغنديروا فيها الفاليو ديال a.add adder which is like هي الفاليو ديال a كاين value 1 اللي فيها الفاليو ديال b right we're gonna add 0 و1 ونحطهم في add اوكي هي a زائد b الاولى غنكريو واحد فاريابل جوج وغنديروا فيها a واحد فاريابل 3 ونديروا فيها b right ونكريو add 1 اللي هي a زائد b جوج زائد 3 اوكي and then we're gonna multiply add مع add 1 we're gonna store it في mul and then we're gonna take mul and divide this by 4 and store it في div and then I'm gonna store div في c and then I'm gonna load c back into a variable called 4 and then I'm gonna return 4 okay so you can see باللي غير ديك اللعيبه ديال a زائد b compute a زائد b it takes 3 instructions then 3 LLVM instructions واحد اخرين so we can potentially could have just did it once right you can see here we could have just did mul into add مع add right then عقلتوا على قبيله قلت لكم كاين واحد الحاجه سميتها strength reduction كنا كنهضروا على قبيله one of the things we can do is like some operators are more expensive division is notoriously معروفه انها expensive right in this case you're dividing by 4 and dividing by 4 integer division by 4 is a nice candidate for optimization you can replace it by a much cheaper alternative okay who has it من غير عزوز I know you have Mehdi
نقدروا نديروا subtractions ونحسبوا شحال مره subtraction
how do you do multiplication by 4 using subtractions in this case and it'll be cheaper
division ماشي
division انت قلتي subtraction ولا جاب لي الله شنو قلتي انت
قلت subtraction زعما
how do you compute this
نبقاو نقصوا 4 ونحسبوا شحال مره نقصنا 4 حتى وصلنا اقل من
No, that's not mathematically correct.
Yeah, I don't think this is correct. Like you okay, let us say غير باش نتفاهموا على واحد القضيه. حنا عندنا واحد فاليو سي بغينا نقسموها على 4. هو هنايا شنو كيدير مول داك افوا بي اللي حسب هو كيديرها على 4. حنا بغينا اوبتيميزيو هادشي. بس ما ندير مول على 4 بغيت ندير شي حاجه اخرى. Right? So whatever you do it needs to be faster من هذه. Okay?
اوكي
نزار
الوغ كاين نضرب في 0.25 ولا سي لا ميم شوز
that's the same قسمتي ولا ضربتي في 0.25 that's pretty much the same حقاش info you involve like floating point arithmetic this is not good this is gonna be slow حيت الهدف هنا I'm telling you this لحقاش هذه is a micro optimization ولكن فاش كتدار بزاف it matters okay شكون كان الاول حمزه
Yes, I think I remember something, but I don't know what's the name. For division, we can do bit shifting.
bit shifting دونك شنو غترجع هاد الانستراكشن شنو بغينا نديروا لهاد الميل
I think shifting by 1 bit equals dividing by 2. So maybe shifting by 2 bits is equal to dividing by 4.
Okay. Mehdi?
So that's it.
The same idea.
Same idea. Okay. So let me see شنو دار الكمبايلر. This is the optimized. And then again, like to this is the unoptimized. This is optimized. Unoptimized, optimized. Like look how many instructions that we are running. دابا 3 د instructions. Right? So and yes, like إلا بغيتي دير حيت عندنا 4 تما we can do shift operations which are much cheaper. If you shift by 1, you divide by 2. In integer space, right? If you wanted to do real floating number operations, there is no, this wouldn't work. So, but if you shift to the left, if you multiply by 2, you can replace multiplication by just shift right, shift left. Then you shift right, you divide by 2. So شنو ولا عندنا هذا عزوز؟
I have an interesting question that you don't have to answer. I think it might be out of scope of this, but just how will the compiler know اللي راه عندنا multiplication a plus b twice? That's something I will look for. Maybe that's a good question to look for as well.
Yeah. You can. I mean, this is like you can encode this as a pattern. Like if you find yourself like doing code replication, like doing the same instruction twice, like you can literally like detect a plus b twice, done in a row. And I guess like أنا نقول لك علاش هادشي like interesting لحقاش sometimes you can this might not happen. Like غير مثلا let's say درتي a plus b درتي ديك الاوبريشن ولكن درتي most منهم درتي اوبريشن اخرى. This might prevent it from being applied. حيت ما شافهمش متابعين.
Yes, you're right.
Yeah, you can only push it so much. You can encode things ولكن sometimes this might not work. داكشي علاش كنقول لك فهمتي تا optimizations examples كيكونوا like I didn't like stumble on this. Like you have to craft them so that they appear to make it the point. But sometimes they might not match.
This is maybe why it's good to learn about these kind of optimizations that the compiler do, because you can write code in such a way that
you can prompt it.
Yeah, exactly.
Okay, so الكود اللي قلنا لنا شنو هو add هو add a و b and we store it in add. مول هي add في add كما قلنا قبيله. So داكشي كامل درناه في two instructions. And then division is left shift right, right? Mul by 2, which is like divide by 4, but this is much cheaper. And then we return div 4. Okay? Questions? Okay. Good. All right. Let's see. Another technique. It's called dead store elimination. And now I have a function, of course, هي الفانكشن اللي بغينا optimize called foo. Foo takes b as a parameter. It computes value a. A equals bar 10. And then a equals bar b. And then we return a. And bar just computes some value based on x. It multiplies it by 2, and then it does minus 10. As humans, again, I'm going to ask you, how can we optimize this? Mehdi.
I think the first assignment ما كاينش لاش يكون حيتاش ديجا غادي نعاود override the value of a, so it should be eliminated.
So it should be int a equals bar b, return a.
Yes.
Okay. Anything else?
We could also like return directly bar b because there's
it's
no
fine.
point.
That's a fine thing. We can have int a كتساوي ونديرو return a. That's kind of equivalent. في الآخر ما غيدير هو ما غيديرش int a كيساوي then return a. We'll just return it. That's fine. But there is something else to optimize. The first optimization هي remove ديك السطر الأول. دابا مازال حاجة أخرى. حمزة.
Yeah, I was going to say to call the function inline.
Inline in the function, yes. That is this.
Yes, inline function.
Yeah, that is the second thing. Inline the function. Because in this case, like the compiler would say, this is like fairly trivial to inline. So we don't have to call into it. The call to a function is tedious. We'll see another more elaborate example about like why calls are notoriously optimized. But you'd need to remember really to call a function. You have to create a new stack frame, right? Push, like do some setup to push your current base pointer, current like return address and whatnot, and then call the function. Then make sure that after you're done, like pop your stack frame, remove any of the residual variables, and then return to the caller. So these adds a bunch of instructions with every call, right? هذه وحدة. ثاني حاجة, if you want to minimize your stack depth, that'd be nice. حقاش كون ما كان stack ديالك طوال, you'd risk hitting your. حقاش stack size is kind of like limited. regardless. So your stack size is not unlimited. It's not like your heap. So you'd want to be within bounds of the stack trace. If you go too deep into stack, you hit like the famous Stack Overflow error. We'll see an example of how this actually works. There's an optimization specifically for this. Super good thing. Let's look at the code, unoptimized code. So the unoptimized code, شنو غيدير? It will store B in a local, let's say local variable. It will call bar with 10, take the value of bar. It will store the value of that it got from call to A, right? We will load the value of B, which is هو الارجيوم اللي كان جانا احنا كنا الارجيوم سجل B. We'll take the value ديال B, we start in the variable 0. We call again bar with 0, call 1, and then we store call 1 to A. We start call المرة الأولى في A, and then we store call 1 out of A, and then we just load I32 pointer A into 1, and then we return 1, right? This is likely to be optimized. Like, we don't really have to care about this. This is not the assembly that there's gonna be. This is yet another abstract layer on top. Now, كما قلنا, like there are two calls هنا, which you likely won't want to have, right? So this is the optimized code, right? Again, unoptimized, optimized, unoptimized, two calls, bunch of instructions, optimized, no calls, two instructions. So shift left B with 1, see? هاي عاوتاني درنا x فوا جوج اللي هي بار اللي هي جاتنا هنا. So x فوا جوج هي shift, قبيله درنا shift right 2, دابا نديرو shift left 1. شوف بحال ضربنا بجوج because it's cheaper. Or shift left B with 1, and then we take this value and then we add minus 10 to it, which is minus 10, and then we return it. Okay? باين هادي. Cool. Let's go on to the next one. Constant propagation. Like, you can do constant replacement, right? You can replace things that are known to be constant at any given time. But constant propagation is about like, okay, what happens after the replacement? Some things might be open to re-replacement, and you want to keep pushing that as much as you can. Like as a human, احنا humans نشوف هذا الفانكشن فوق، نشوف x كتساوي 10، نشوف عندي 5 ناقص x على 2 ديرها في y and then return y فوا 20 على x زائد 2. I'm doing some math, and believe me, this is all that programs do, all those math, right? So I can look at this and see, okay, so at x 10 شفتها ما تتبدلش. y كتساوي 5 ناقص 10 على 2, which is 5 ناقص 5, which is 0. And I'm multiplying 0 by something, which means غير تورني هنا 0. Which means the optimizer could look at this, and after احنا replacing 10 هنا واعتبرنا هذه effectively constant, I can re-evaluate عاوتاني ونشوف بلي okay, so now y is 0, and then anything اللي مضروب في 0 I don't have to even compute. So my function becomes effectively x equals 10, this is dead code, y equals 10, this is also dead code, and I can just return 0 always. باينه هاد transition من هنا لهنا. Right, now let's see something that is slightly very nice, but is kind of hard to understand. So there is شو اللي ما عمره سمع بتيل call optimization، اللي ما عمره سمع بها. I'm assuming a lot of you سمع بتيل call optimization. عزوز ما عمره سمع بها ماشي عمره سمع بها. Have you never heard of tail call optimization? I'm kind of surprised.
Maybe the name, maybe the concept I know it, but the name
Okay.
it's not on the top of the stack.
Okay. Tail call optimization is an optimization that some programming languages added. A lot of functional programming do it. C++ do it. Java doesn't have it. The optimization is based on if you write your function in a very particular way, the idea is that I can replace the nested function calls with reusing one stack frame. Just one single stack frame. I don't have to create a stack frame for every call. I don't even have to have calls. As long as the function itself, the recursion, is the last thing that is being called. This implies really all the setup, like عندك a recursion depth of 100,000. So the 100,000 recursion depth actually is just one stack frame. It's not 100,000 stack frames, it's just one stack frame. So all the shenanigans that you have to do to like set up the stack with every call and then reset it after every call, you don't have to do it anymore.
So this will end up being like an off-one memory kind of like footprint, or no?
Off-one is a big word. This will prevent the code from generating all the code for changing the stack. So the tail call optimization is the idea of like reusing the current stack frame. So I don't have to علاش كنكريو other stack frames. We need to keep the information the local variables of the current frame and then call into the recursion, and then when we get back we want to still have access to those. حيت I might still want like تخيل ما عندك DFS عندك int A كتساوي 0 DFS and then int B كتساوي لنا الريزولت نتاع DFS مضروبه في A في الاول. It means باللي once you went into the other stack frame you still wanted the results and the local variables اللي كانوا عندك at the time of the call. إذا كانت عندك آخر حاجة درتي هي the recursion, in that case you know باللي you don't need anything else because انت من تما غتخرج. So the optimization is okay, since هذه هي الأخرى I don't have to create a new stack frame, I can just reuse this because I'm never gonna reuse anything else. ما عمري غنعاود نجي لهنا ونعاود نحتاج داكشي اللي كان الفوق. Right?
Therefore it's kind of like the same kind of like stack frame. ما نعاودش نكري واحدة أخرى.
No, I'm not. This is the optimization. Is that not create extra stack frames. So the famous example for this, which everybody uses, which I'm gonna use as well, is factorial. إذا عمرك كتبتي factorial بحال هكا, well, nobody writes factorial recursively anymore. But if you do, in some languages, right, this will be super fast. If you write this function in Java, you will blow up the stack. Right? If you don't use this, if you write it like this in C++, ولا Scala, ولا something that actually supports tail call optimization, you can get away with it. All of this will be translated into something that looks like a loop. We'll see an example of how this will look like. Okay, so الحاجة اللي نعقلوا عليها هي we have a function that takes n and takes some accumulator value. This usually starts at 1. So إذا كان n صغر من جوج, we just return the accumulator times whatever the value of n. Otherwise, we just keep on going like from factorial n plus 1, n minus 1, and then we keep like doing the accumulator times the current value of n. So احنا بغينا نحسبوا فاكتوريال, كلشي كيعرف يحسب فاكتوريال. هذا الريكورجن شد تيخصص فاكتوريال. عزوز.
So واحد الكليم اللي I will make دابا هو was correct ولا لا. That means really most of this is a very important optimizations the functional programming languages كيخدموهم, because otherwise they don't have loops. The only way you can do loops is through recursions or tail recursions. Okay.
So لما شتي OCaml and شتي Haskell, they will probably provide you some guarantees about like tail optimizations. يكون عندهم شي section في الcompiler reference ولا شي حاجة كيقول لك oh these are the guarantees that we provide for tail recursion. For كاين شي languages اللي كيقول لك okay plain we don't support the optimization. Yeah, we can't really detect it. Okay, so إلا عندنا واحد function اللي مكتوبة بحال هكا, the thing to keep in mind هي أن هاد الfunction we have recursion ولكن آخر حاجة we do is factorial. كنا كتبنا مثلا n ما كانش عندنا هذا accumulator هنا ودرنا n times factorial, this wouldn't be the last one, last operation. أولي خصك فهمتي تمشي تحسب factorial عاد ضربها في n. فاش ترجع من الريكورجن خصك دير شي حاجة أخرى. Which makes this not tail call optimized. في هذا الكيس هذا the optimization is valid لحقاش we know آخر حاجة غنexecute هي the call to the function. So anything else here wouldn't be valid anymore. Let's look at some code. So this is the unoptimized. This is the unoptimized IR. So we start at entry, right? I'll go back and forth between the code in here باش نعرفوا شنو كنديروا. So the entry loads the value of n into 0. And then compares the value ديال n وجوج. This is here. Right? And then based on the result of this comparison, we do a branch instruction. إذا كان صغر من n صغر من إذا كان صغر من جوج إذا كان صغر من جوج go to if then. إذا كان ما كانش صغر من جوج go to if end. Okay? So إذا كان صغر من جوج, in this case this bit right here. So we load the accumulator, we load n into 1 and 2. We multiply 1 and 2, right? And then we store the result into the return value. And then we
By the way, it's a return, not an int. It was if you go back to the code, the actual, if n is less than 2.
Yeah, it's fine. Sorry. That's the fixing a bit. But this is if شي حاجة return. So we store the value in the return value, and then we break or we branch into the return label. Yeah. The return label, all it does is like it creates a new intermediate value called 6, and it will get like the return value loaded here, and then return the value 6. So this is doing this. نرجع لنا. If not, صغر, then we go here. So this will load n in 3, subtract 1 into sub, take n and takes the accumulator into 4 and 5, multiply them into mil1, right? And then it will call factorial of sub or mil and take the result and return it into call. We will store the results into a call for return value and then do the same by breaking into the return. Okay? باين هذا الكود هذا اللي كيحسب فاكتوريال. إذا ما كانش باين somebody let me know باش نعاودوه. Important bits to keep here is that هذا لاحظوا ان هنا there is an actual function call. Well, the optimization is that we want to remove this function call. Ideally the function call ما خصهاش تبقى. حقاش إذا كان a call instruction it means بلي داكشي اللي ما باغينش نديرو غنديرو. We will create stack frames that we don't want. So this will create all the stack frames and all the shenanigans to make it work. So if you take this and like pop it into some assembler that will try and generate assembly from this, you'll see the setup into a stack pointer, base pointer, like the new stack frame, and then the cleanup in between. Let's look at the optimized value or the optimized code. So this is the optimized code. So the entry, right, is we branch into tail recurse. Okay. So tail recurse is again أول حاجة كنقولوا هي n. We have a value n اللي هي هذيك 5 function ديال قبيلة اللي قلت لكم. I told you about like 5 functions which will assign values based على حسب منين جاي انت. So إذا كنتي جاي من entry, which في هذا الكيس احنا جايين من entry, ياك نديرو فيها n. so n كتساوي n basically. accumulator على حسب منين جاي. الا كنت جاي من entry غندير فيه الاكيوميليتر الاوريجينال فاليو ديالو. okay and then I compare n مع جوج and then I branch again. if then otherwise. if then can multiply accumulator و n, right? and then I return I32. I return the value. كنضرب accumulator في n وكنريتورنيه, which is basically this, right? if not, which is this bit right here, we just do sub, which is adding n ناقص واحد. so كنديرو n ناقص واحد في sub. مول 1 هو مول مضروب هو ديال accumulator في n. so we compute had two values n ناقص واحد و n مضروبة في accumulator, right? and then we branch again to tail recurse. there is no call instruction. we just branch into tail recurse. لا tail recurse شنو غدير؟ وإلا كنتي جاي من entry دير فيه n, لكن هاد المرة حنا جايين من if end, so غنديرو فيها sub which is هاد الفاليو. so n غيولي دابا هو n ناقص واحد, right? accumulator هو إلا كنتي جاي من entry هو accumulator. إلا كنتي جاي من if point end هو ميل 1 هو هادشي اللي حسبنا هو n مضروب في accumulator الأول اللي كان n. and then we have to do it all over again. at some point غنكونوا صغار من جوج and then we will go here وغنخرجوا بالملتيبليكاتور. this is kind of hard to follow maybe at first, but like it's the important bit هنايا هو ان هذه ما كايناش. there is no call function. okay so which means باللي هذه actually looks something like this. if you write it in code هكا ولات دايره. we take an n and an accumulator as long as we are صغر من جوج كنضربوا داك الاكيوميلاتور في n وكنقصوا من n واحد. then we keep continue on doing this. في الاخر كنضربوا الاكيوميلاتور في n وكنخرج. so we moved from something that looks like this into something that is completely linear في one stack frame.
Is it a while or do while? Not 100% sure. It's kind of like the same maybe.
I don't know. This is approximative code. This should have like the same behavior. Now you can think about it as a do while instruction. You can think about it as a while instruction. It doesn't really matter.
The reason I say do while is because you have the do من كتدخل من entry and then you do kind of like if else and then you go back to.
Yeah, which means إذا كانت هذه false في الأول راك غتحسب هذه.
Yeah, cool. Yeah, sure.
Does this make sense? This is one of the hardest optimizations, hard to see for people at first, but if you look at it a couple of times, it becomes like more obvious. All right, dead code elimination. We have this code, right? We have a const. This is similar to things that we've seen before. So we have x, a constant that is 10, b that is something that computes something. We have our function foo that does this. As humans, tell me شنو من الحوايج نقدروا optimizeوهم. نزل.
Move some of the smaller code from other functions directly to foo.
كاينه فانكشن اخرى من غير فو اللي هي b.
Yeah, like the computations from being those initial foo.
Okay, so you want to inline this basically.
Yeah.
Okay. Is it? Mehdi?
I would say هذيك ال if statement ديجا تكون زيرو so البلوك اللي وصلنا ما غاديش تيكزيكوتا so we could eliminate that code.
Okay. So there is no point in inlining?
Yeah, we could wait. Yeah, which means that B is not called, which means we can eliminate B also, I think.
Okay. Azus?
So I think multiple levels of optimizations maybe. So depends. If B is being called somewhere else, man, so that's going to be in line with the class. If it's not called at all, we can remove it. But if the if statement can be scrapped, that means the C is going to always be 10. So we can even align for niche and 10, return 10.
Yes.
So we can have a return 10 statement.
Yes. But can you think about one thing قبل ما نوريكم the unoptimized code is think about, okay, you are a human, you have a very complex brain to do this. Like think of a program actually trying to do this. Like think about how cool are optimizers, how complex how can an optimizer be, and ديما كيقدر يديتكت هذه. He can always detect this and just remove it. Hamza?
I think the whole foo function can become a variable equals 10. Just return this.
Maybe it's maybe على حسب اليوز كيس ديالها. But from this from a foo ما كنشوفوا فيها from foo غنخليوها function. For our intents and purposes غنخليوها function. But like if you can think about it getting used في شي بلاصة أخرى, you can think about it as like just scrap foo and just replaceها ب10. And you don't even have to call foo. So yes, that's a further optimizations for the optimizer to see. The point علاش وريت example نتاع the code elimination, because also it's easy to reason about, but also like it's very hard to reason about. If you think about it from an optimizer perspective, how would you detect this? Detecting this is fairly hard, and you can think about it from multiple levels. ماشي غير من level واحد. Because this could be happening like at a multiple level, and the compiler would be able to optimize this away for you, which is really cool. So without optimizations, إلا ما كانش عندك an optimizer, you would have like code that looks like this. You would store the 0 in Y, you would store the 10 in C, you would still load both of them and do the multiplication, convert to a Boolean, and then decide whether to actually call B or not. And at the end, whether to return the value like from C or not. So this is like fairly expensive. Right? حسب غير فاش تحسب expense حسب ايش حكينا من instruction. This is the optimized code, literally. Like you have one instruction, return 10. So an optimizer can move you from this to this. That's why optimizers are very critical in software. And we can't have software that operates بلا بيهم. بلا بيهم, like our programs would take ages. Wouldn't be able to roll them. All right. Closing notes. Optimizers are very complex. Actually, they are very complex pieces of software, very hard to reason about and very hard to make. That's why nobody makes optimizers anymore. Most people just rely on LLVM as the platform. You can build new programming languages. It's very hard to make optimizers because you'd have to make something that is better than the 20 years of experience اللي محطوطة في وسط LLVM, which is very hard to do. And then the way we got to this course, Aslan, well, by going to a tool like Godbolt, or any tool that looks like it, dump some code, and change the optimization levels. Look at the LLVM IR generator, and look at the assembly, and experiment about like what is actually going on. Like, why is my function getting an optimization level 0, I get this much code. And at some moment, if I toggle optimization level 1 or 2 or 3, I get this much code scrapped away because my optimizer kicked in. So experimentation is crucial to understand better optimizers and to be able to write more performance software. Okay, so I'll leave you with this. This is all I had for today. If you have questions, let me know. Otherwise, we can call it a day, and then we'll take a 5-minute break and join again in the next call with Azuz, who's going to talk about time.
I'm sure the other call, yeah?
Yeah, just go to the other call in 5 maybe.